Very good. Okay. Good morning, everyone. To this C in C++ pre-course lecture, we're going to be looking into procedural programming and code organization today. Now, what you've been taught so far, mostly, I think, is well, you've probably heard that these high-level, what we call high-level programming languages like C, C++, Java, Python, etc., give you a human-readable language, which then gets translated by a compiler into machine code, which the computer is actually able to execute to run the program. So, what I think you've been taught mostly so far during this course was basically the essential building blocks of C and C++, of C and C++ languages, meaning you get the keywords that the compiler understands and knows how to translate that. So you get the essential building blocks of how to use the language. And today and on Thursday in the object-oriented programming session, we're going to step away from that a little and look at things which are a bit further down the line than just translating certain instructions into machine code and running things. So the idea being is eventually you need to start thinking about not only what code you write, but also how you write it. When programs become big enough and complex enough, you want to really start thinking about the philosophy of paradigms, how to write good code, maintainable code that will live for a long time, code that developers can work with and onboard quickly, etc., etc. So this is what procedural programming and code organization is going to be about. And what I have in mind for you today is we're going to do a really quick introduction and as a quick aside look into how we deal with command line arguments, because that will come in handy for certain exercises. And we'll also look into recursive function calling. And a second part of today's session is going to be on code organization, how to deal with header files, how to split your code in multiple files, and associated with that the external and const modifiers and keywords, and finally how to use external libraries and what they are good for. So let's start with procedural programming in general. Now, structurally, so historically, it follows from approaches or paradigms which are called structured programming. So most programming languages, especially the early ones, were procedural. There's a kind of a super class of these methods called imperative programming, where the idea is you give the program instructions. You instruct it what to do line by line, code by code. And this may sound like quite obvious to you, which, fair enough, it sort of is. But the idea of procedures is, or procedural program is to make use of procedures. So you pack up blocks of code into functions or routines. And structural programming comes also from that, is you pack bits of your code in separate modules or in separate files. So you encapsulate them in this way to divide and conquer, what they call it. So you separate your program in different chunks, which are then called during runtime. Yes, so technically imperative programming is a slightly older paradigm, but since they are kind of similar or have a lot of similarities, procedural, structured, and imperative programming are often conflated. The idea being we are providing instructions to the program, how to modify the program state line by line, or in this case with procedural programming by introducing procedures and structuring our code into procedures. Now, the idea behind procedural programming, what's the main idea behind the paradigm, is to make use of modularity and scoping to improve the readability of your code and reduce its complexity. So this is, again, to emphasize, this is not for how to get, fast code or how to get better optimizations type of thing. This is how do I structure my entire project such that it is maintainable and actually usable, and I can actually do something with it. So modularity here, we mean a systematic division of some complex code into smaller modules. This reduces the complexity of a program and makes it easier to find and edit any part of the code if required. Now, scoping, on the other hand, refers that the block or the region of the program where some variable or some function is declared, defined, and used. And these are two closely related concepts, as scoping is actually used to implement modularity. So ideally, what you want to have is bits of the code, but nobody else or no other code is touching, and all you're doing is providing some sort of interface between them. Now, we can start comparing procedural and object-oriented programming. We'll look into object-oriented programming a bit more on Thursday, but the main object-oriented programming is also a programming paradigm aimed to help you how to think about the problem, how to define and declare a problem, how to encapsulate data, and how to structure a program. So, in procedural programming, we have data and functions, and those are two distinct elements of a program. Right? In object-oriented programming, the approach is, however, quite different. It is to say, look, I have this thing we call an object, and that encapsulates both data and functions which will operate on the data. So no function outside of the object is operating on the data, just whatever is inside this object or class, which we will talk about later. Now, technically, in procedural programming, variables have global access. So any bit of the code can touch any variable in principle. For object-oriented programming, however, we specifically introduce specifiers such as public, private, and protected to permit developers and users, so not the compiler, whoever is writing the code, to permit them to access certain data or prohibit them from access certain data or functions. This is also in order to help structure code. This is the bit you're supposed to touch, looking from outside. These are the functions you're supposed to touch, these aren't. Therefore, I am prohibiting you from touching them at any point. That's why we have things like these private restrictors. And finally, procedural follows basically a top-down approach to programming. So you start from the top level and get more and more specific until you are doing what you're doing, specifying the entire algorithm along the way. Whereas object-oriented programming is typically a bottom-up approach, where you start by defining your class or your objects and start building from there, whatever you need to do with those objects. Now, we can also compare procedural with functional programming. Well, procedural programming specifies steps that a program must take to reach some certain desired state, while functional programming more or less treats programs as evaluating mathematical functions. And functional programming avoids states and mutable data. And finally, functional languages also have lazy evaluation, so they only get evaluated right in time. So, what do we have in mind more concretely for today? With procedural programming, we want to give you some ideas how to structure a code, which includes recursion. We are going to briefly touch upon how to understand the speed and memory consumption of your code. Then how to modularize and scope your larger programs, how that can be done using, for example, header files and splitting your program into multiple files. And finally, also how to make use of external libraries. Now, for what we're going to do, and for a couple of exercises we have in store for you, especially in the mini program, it's going to help to know about how to pass command line arguments, or how to parse command line arguments. Command line arguments, I'm sure you've encountered them before, but if you're running a program on your terminal, for example, you can pass them flags. So you have seen, for example, the GCC compile command, how to compile with GCC, and we would pass GCC and then your file name you want to compile, like foo.c, and then -o to output a file, and then we'd have whatever the file name is, myprogram.exe or something like that, right? So GCC would be the program name that we're executing, and all the rest, like foo.c, -o, myexecutable.exe, those would have been command line arguments, because we are providing these arguments to GCC. So how do we do this within C or C++? Well, we access them through the main function. So you remember, every program needs to have a main function. However, there are two permissible signatures for the main function. So one is this, just int main with no arguments, and the other is we pass it int argc and a pointer to pointers of type characters, so basically a list of strings called argv. And this is the essence of how you're getting command line arguments. So this argc here, it's an integer which specifies how many inputs or command line arguments the program has been provided at execution time. And argv is an array of strings that contains all these inputs. Now, here's a very important one, something that you will likely trip over all the time because it just keeps happening. By convention, the 0th element of this argv array, so the 0th element, the very first in the list, is always going to be the program name. So if I compile this program and run it as myprogram.exe, argv0 is going to be myprogram.exe. Now, usually I'd ask the audience right now why argv, so the argc argument of argv, of the argv array, is a null pointer. But today I'll just answer it for you. Well, the answer is because at argc you have run out of arguments. You have no more arguments left. So that always has to be a null pointer because there's nothing there. Now, when are we using command line arguments? Well, they are quite useful when you want to control your program from outside rather than hard coding the values inside the code. Or an alternative would, what most people commonly do is, for example, write some parameter file which the code needs to read in. But for certain cases, for certain use cases, it is much easier to run it via a command line flag. Now, alternatively, you can use the scanf function to either prompt the user or to type in some reply to you and then parse that. Or again, you can write a parameter file you could read. But command line arguments do come in handy, I can tell you that much. And a piece of advice about good practice: always, always, always check your input before continuing. So if you read in a command line argument and you expect it to be something, make sure it's actually valid input, because really bad things can happen. Okay, now we are about 80 minutes in. I think we can go through recursion as well. Right, so the second point I wanted to talk to you about before we get into the actual code organization is recursion. Now, what do we mean with recursion? Well, in principle, functions are allowed to call themselves while still being evaluated. So we're calling a function within itself again. And so every time a function gets called within itself, it gets a new copy of all the stack variables. And here's another bit of advice. This, in principle, if you're not careful enough, you can create an infinite loop which will then crash when you run out of memory, because every time you call a function within itself again, it will allocate a new stack for it. So it will do that indefinitely until you run out of memory and your operating system says, nope, no more memory, I'm out. Kill this program. So something you need to do is implement a termination criterion. When does the recursion stop? Now, here's another piece of coding advice. Always start by writing the termination criterion when writing a recursive function. Always start with that, number one. And number two, you can keep track of how many times you recursed by adding a new parameter, like an integer, how deep you are in the recursion tree. And you can, and every time you call a function, you just increase it by 1 and add like an emergency exit. If you reach a depth where you're absolutely certain you shouldn't be, just shoot yourself a warning message saying something is going wrong here. That's just some advice from somebody who has walked into infinite loops way too many times. But yeah, so why do we want recursion? Well, it's actually a very, very powerful tool used in a lot of applications, such as matrix block algorithms, some multi-scale basis systems. If you have refined trees, tree walks, where you split, let's say, a volume into finer and finer cells, so you always split the dimensions by half and by half and by half and by half. You just recurse. You can walk the tree, so visit all the cells, which are all the smaller and smaller and smaller, by writing a recursive function which goes down and down and down and down. So let's look at an example. Let's write an algorithm for the greatest common divisor using a recursive function. So let's call this GCD, greatest common divisor, where we pass it two integers, and it's supposed to compute the greatest common divisor. Right? And then, test it, and as an exercise, try and plot the trace. Try and plot what's happening. So I'll leave the exercise to you. But to discuss what the basic algorithm is, if we have a modulo b equals 0, so if we have a division without any remainder, then b is the greatest common divisor. Otherwise, recursively call itself, but swap the parameters. Instead of a, b, you call it b and a modulo b. Now, we don't have time to go into the derivation of this algorithm. Just trust me that it works. I'm pretty sure it's explained on Wikipedia. It's called the Euclidean algorithm, so you can look it up. It's not very tricky to derive how it works. But so let's look at our implementation. So here's our code. GCD, we have integer a and integer b as parameters, and the very first thing we do is the termination criterion. So if we end up with b equals 0, we return the other value. If we end with a equals 0, the solution is going to be the other one. If neither of them is 0, then recursively call yourself with b a modulo a. And here below, just the function, just a main and how we can call it. Right. So, at this point, we have to wonder, well, how efficient is our calculation of the greatest common denominator? Well, in the very worst case, the algorithm is going to go through a number of recursive calls, and the number is going to be equal to the number of modulo operation it takes to reach the base case, which is 1. This turns out is logarithmic in the number that you're trying to find the modulo of, the greatest common divisor of. So the time complexity is going to be in the order of log n, so in some way proportional to the logarithm of the number you're trying to find. Similarly, remember, every time we call a function recursively, it allocates new memory on the stack every time for the variables this function needs. So it's also going to be proportional to order log n, because we need the stack for each recursive call. Now we can differentiate between different types of recursion. Let us start, for example, with linear and nonlinear recursion. So we had, for our termination criterion, we have an if-else case. So if some criterion is reached, we're at the end, we're terminating, right? So it introduces a leg for each case. And the base case just returns, instead of calling the termination criterion, simply returns instead of calling the recursive function. And again, very important in order to avoid infinite loops. Now, we call a function linearly recursive if we have at most one recursive application of the function in the expression of any leg of the definition. So we call it only once. If we have two or more, we call it nonlinear. So maybe it helps to look at this with an example. Let's say we want to use recursion to implement computing the Fibonacci numbers, where the 0th number is defined as 0, the first number is defined as 1, and then the nth number is defined as the sum of the previous two ones. Right? And you can already see what's going to happen here. Since we need two previous ones, there is an opportunity here to call it twice, to call the function recursively twice. So f0 and f1 here is what we call the base cases, and the recursion is going to calculate the Fibonacci number that we're looking for. Now, we can write this as a nonlinear recursion. So naively say, okay, if we're at 0 or 1, meaning n smaller or equals 1, we return just the number. That's the base case. Otherwise, we return the sum of the previous two numbers, where we compute those recursively. So this, for example, is a nonlinear recursion because we have two recursive calls. But what happens here is, if we have some input which is greater than 1, so something where we actually call for the recursion, what happens here is, every time these two new ones get called, they will keep recursing down, all the way down until the base case. So what we in fact will be generating is, so after a first split up, on the next iteration, two of them are going to split up again, and then two of them are going to split up again and again, and all of them are going to be split all the way to the bottom, to the base case. And what you're essentially getting here is a tree recursion. You get a tree structure, like a binary tree, and this is why we call it a tree recursion sometimes. Now, instead, if we think about the problem for a little longer, what we can do is write it with a linear recursion as well. Meaning that, well, take a look at this algorithm. If we have the case n equals 0, so that's our base case, we return the value that we have here, int a. Otherwise, call yourself recursively, but decrease n, so go n times back. While this parameter b here is going to be always incremented. So we're going back while adding stuff up going backwards. So we are essentially computing them, the Fibonacci number, backwards, even though we're starting from a bigger number. Now, the base case, here is not recursive, it simply returns. And the other ones, right. Now, let's talk again about the time complexity. Now here for the nonlinear recursion, so the one where we call the Fibonacci sequence, the function twice every time we recurse, the time complexity is not good. So because each recursive call spawns 2 new function calls, so that's going to be a lot more computing than you actually need. But the overall time complexity, so the overall time complexity is going to be in the order of your actual Fibonacci number that you're computing at the end. But the memory requirements, they're actually not terrible, because the program only scales with n, which is so the nth Fibonacci number, because you're not, even though you're calling the function twice in every recursion, you're not going to solve them in parallel. So you're going to solve them one after one, and only after one has finished. So you're only scaling with order n, because a new stack frame is needed only for a recursive call, and this goes only to the depth of n. For linear recursion, however, the overall time complexity is going to be of the order of n, so the nth number, because we will end up doing only n computations. And this is because we are replacing this expensive double recursive call with a simple one. But what about the memory requirements? Well, kind of the same. Because we replaced it and are only doing essentially n steps, it will be proportional to the nth, to order n. So it will go with order n. So one of the advantages of linear recursion, why it is much preferable in scientific computing, is we can pretty much always translate a linear recursion back into loops, and in fact the compiler can do that for you. The advantage being loops can be very fast to solve, comparatively at least. So converting a nonlinear recursion loop, however, is very tricky, sometimes impossible. So it's not an easy endeavor. So if you can, look out for a way to solve it using linear recursion. Now, we can also differentiate 2 different types of recursion between backward and forward recursion, not just linear and nonlinear. A backward recursion, we call it backward if the recursive application, so the point where you're calling your recursion, is embedded within another expression. So, for example, in our Fibonacci case, where the nonlinear one, where we call it twice, the expression is compute one leg of the Fibonacci and then add it to a second recursive call. So that will be within an expression, that will be a backwards recursive expression. So during the execution, what the programmers do is, once it arrives at the place where it's being called recursively, because we're not done yet here, we need to keep the stack of everything before us as well, while going further down. So the program must preserve sufficient information from the outer call environment, so once the recursion is complete, it can finish up the evaluation. Whereas with a forward recursion, we call it if it's not embedded within another expression. It's like our second call for the Fibonacci, where we only get, we don't need to keep track of stuff in there. So the outermost expression of the, so the outermost expression is going, so that there where we recurse down, and any other will just appear in the argument list themselves, so we don't have to keep track of the entire stack anymore. Okay, so we're gonna leave these exercises to you to play with. We did the Fibonacci numbers. Another fan favorite for getting practice with recursion is to write factorials. So write one which is forward recursive and write one which is backward recursive, and try to look at and visualize and understand what the call stack is going to look like and which variables are going to be stored. Okay, so if I remember correctly, it should be one of the last ones, talking about tail recursion, one very special case. If it's both forward recursive and linear recursive, that's what we call tail recursion. So essentially, if it's the very, very last thing of a function that the function does is return a recursive call of itself, which is in a linear fashion, that's what they call a tail recursion, right? So, is a Fibonacci implementation tail recursive? The first one, the non-linear one, no, because it's not linear. The second one was. Now, again, why do we like tail recursions? They are easy to compile into efficient loops, and the compiler can actually recognize that and help you with that. And the states of unevaluated expressions, we don't need to store them, so higher up in the stack frame hierarchy, so we can return the result directly, and we're going to be done. So once you reach the bottom of the recursion, all you need to do is pass it along to where you started, and you're good. And sometimes they can actually, the compiler can help you with that, especially when higher optimization levels like 02, 03 are enabled. And GC should have these additional flags, so they will be typically embedded within those. So -02, -03, -OS will be a shorthand for a whole range of flags, and these will be in there. So if you want to specifically tweak that behavior, you can use these flags. Let's move forward to code organization with the sense of procedural programming. Now, the problem is, so we just had an exemplified image with Margaret Hamilton in '69 standing next to the code she and her team wrote for the Apollo mission. Now this looks like a lot of code because it is, but I can tell you modern projects are not really shorter. So you still will have to deal with these amounts of code. Like I've easily seen codes with millions and tens of millions of lines of code. So once you get to those, even a few thousand lines, it starts being enough to become unmanageable. So the idea is, once you start building a larger project, what you want to do as part of keeping things manageable and maintainable and sustainable is to split the implementation up into separate files. So again, modularity and scoping, right? But how do we do that? How do we manage these files, and how do we split up the functions into coherent units? Well, that's a very debatable question, and people will argue about it all the time, what the sensible way of splitting them up is. But as long as you follow some sort of rules that you basically self-impose, some sort of standard that makes sense to you, you will do all right. But here, or in this session, we're gonna look more into how is it actually done. So how can I actually split my code into several files? How is that done? How does that work? So to begin with, just a quick reminder. In C and C++, we distinguish between a variable or a function's declaration and definition. Now, declaration is telling the compiler this name for a variable or function, or the symbol is going to be available, and it's going to have this signature, right? So it could be an integer of type, so an integer with the name my integer, or it could be a function which returns a void and takes this, and this parameter, right? So we define these. This would be a declaration, right? What names are out there? Now, a definition is actually where this name is stored and what it contains, right? Now, to run a reminder again about scope, we have two specific uses of scope in a specific file. So in any single file, we have global identifiers, which all functions in one file can see, and we have local identifiers, which are only visible in code blocks. So, so anything outside of them cannot reach them. So what do we do when we have larger programs, larger projects that need multiple source files? How do we manage the scope between those files? Because the scope is not going to be available usually outside the file unless we make it so. So how do we make it so? Well, functions and variables need to be declared, that's what we said, before they're used. But what we can make use of is that we can define them later. And this later can typically be at linking time. So, here for example, let's look at this sample code. This void func here with some function body, we do something in here. This is both a declaration and a definition, because we don't declare it anywhere else before, but we already define what it contains. Right? Now, if we call the func, our func here in the main, typically what happens, neglecting all sorts of optimizations which can take place, but typically what happens is while a program is running, executing on the CPU, there is a register or a tiny bit on the CPU which is called the program counter, which keeps track of where in the instruction stream we are. So which instruction we have just executed and what the next is supposed to be. And what happens here, typically when a new function is called, there's an instruction for reset the program counter, get the instructions from this function, and then execute that. All right? So this just internally, and this is something we're going to make use of now. So let's say that in our use case we want to split the file up into several files, because this is a very simple example with just 6 lines of code. Now let's imagine we have 6 million lines of code we want to split up to make it manageable. So to do that, C and C++ use what we call header files. Now, and this is going to be the section about the header files. Now, looking at how to deal with multiple source files. Well, in principle, a C program can be divided among any number of source files. And by convention, these source files. So, by convention, a C program can be divided among any number of source files, and by convention these source files have the extension .c. Now they don't have to. If you want to call your file myfile.b and tell GCC to compile it, it'll work. So you don't have to, but other external tools will be happy about if you follow the convention, especially some building tools and things that help you compile stuff. Now, each of these source files will contain parts of the program, which primarily will be definitions of functions and variables. But one of the laws which you need to follow, otherwise the compiler will be very, very confused. If you want to create an executable file, so an application out of the end which you can execute, one of these source files must contain a function called int main, because that's going to be the starting point of the program by definition of the language. So it's going to be the entry point of the program. So that's the bit you must have. One of those files, it doesn't need to be called main.c, it can be called whatever you like, but it must contain int main, alternately with the command line argument specifications we had earlier. Now, as you may have noticed or suspected, splitting up a program between different files can come with a bit of complexity. So, because again, variable and function scope are only within a single file. So what do we do? How do we deal with that when we split it up over several ones? Well, so yeah, how can we call a function in one file, call a function that's defined in a different file? Or how can some function access some variable which is actually defined and stored in a different file? How do we do that? So how can two files share the, let's say, same macro definition or same type definition, or use the same functions from a third file? Because that's stuff we want to do, right? So let's look at an example. Let's say we have three files called a.c, where we have some function. We have a file b.c, where we have a second function called bar, which calls func, which is stored in A. And we have a third function called t.c, third file called t.c, which is a function tar, which also calls function func, right? So if we just try to compile this, well, why is that not going to work? Well, several reasons. One, okay, in principle we can compile it, but not into a executable, because there is no main.c. So you can compile it into an object file, but if you just compile all the three .c files, what's going to happen is, so the problem being that both B and C need func, which is in a.c. So what we can do, we can try and be clever and include the concatenation operations to add it, to essentially add func into both B and T. But then when we start linking them together, the linker is going to say, well, hold on, you have a func both in B and in T. I don't know what this is. You have defined the same name symbol twice, or the same name twice. I don't know what to do with that, right? So instead, what we can do is start using declarations, right? So now, instead of just using func.t and using some macro magic to include files and concatenate files, we're going to declare functions first in B and C. So we're going to declare, there is going to be a name or a function called func, which returns void and takes an integer as a parameter, right? And we do this in B and in T. And what happens here is the compiler will see the declaration and say, okay, so there is this name called func, but you will tell me what it exactly is and what it contains and where it is stored later, so I can work with that. So firstly, all of this will compile nicely. it'll work, and it will link nicely, because by providing this declaration, so note we have here no curly brackets in here, which would specify some content of the function. So by telling it, look, we only have a name here, so this is a declaration, the actual content will come later. That's what the linker will do. It will look for which names, which contents are still missing, and then find them later. Well, find them during the linking process and put them in. So, yeah, so this time it works out. Now, in general, how is a program structure supposed to look like? So we've seen now you can forward declare things, and this is what we typically do in what we call header files. So they're, suppose we use the same example to store the function func somewhere. What we would do, so the main idea behind how this thing works is to use what we call a header file. Now header files are just C files. So they just contain C code and nothing else. But they're special because we use them for a specific way. Again, there is very little prohibiting you from writing just regular C code in there. In fact, it is just regular C code, but the use case for header files is to keep the declarations in there. And the main idea behind that is to actually also save you a lot of compiling time. So for example, if you change the contents of the actual contents of the function, say the definition or in func.c, which is traditionally stored. So same name, So same base file name, so func and func, header file, associated header file, and associated base file is .c, right? If you start changing some contents of your definitions, of your function definitions, you will need to recompile the entire thing. Now, this would mean if your definitions are in the header instead of just declarations, if the definitions are in the header, then any other file which includes the func.h header would need to be recompiled as well. And that's not what we want. Ideally, what we want is only to redo the linking step, not both the compilation and the linking step. So that's why by convention, headers only contain declarations unless you have a really good reason why not to. While in the associated base file, so the func.c, you include those declarations. So use the include macro keyword and you include the func.h file. What include does, so it is literally this pound symbol include, and then here we are starting with double quotes, not smaller sign, greater sign, because there are not system libraries. You're including local files, so you can actually put in a full path here, assuming it's in the same directory. You start without it. So what this include does is quite literally copy-paste whatever is in func.h and put it into your file while compiling. So you don't see that. You see it as two nicely separate files, but the compiler sees is that copy this entire thing into this file and then move on with the compilation, right? And so this source file is going to contain all the global and private functions and variables that we need. And finally, as I mentioned before, we need to have one, and usually it's called main.c, but one file that contains the int main call, which is the entry to the program, right? So it should at least contain the main function, ideally not too much else. So you can have a really nice separation and into files where you're going. But if you want to call func or your void func int a, so that the function you're defining here, you also need to include func.h in here. Okay, so to sum things up, the header file is typically used to split declarations from definitions. Declarations go into the header, definitions go into the base file. Now, good header will contain comments, and other editors and developers will going to look at it frequently. And again, by convention, it's typical to have per header one base file or implementation file using the same name, just a different suffix. So instead of .h, use .c. This way you instantly know what the associated files are. Now, every C and C++ file and every Unix installation, so all of these come along with many header files. You can look at them at, for example, /usr/include. That's where typically headers go. And some note of caution, some libraries, such as the Eigen library, used to compute eigenvectors, eigenvalues, things like that, are actually supplied as header files only, so you don't actually need to install them. You can just directly include the headers and the code is good to run. Now, since we've been looking into splitting program into multiple files, now we need to look more into the extern and const modifiers. Now, so when So when we split variables in functions between files, we want to be able, or we need to be able, to separate declarations and definitions similarly to what we've been doing with the header files, right? Separate declaration and definition, but sometimes a bit more complicated scenarios can occur where you're not gonna be easily able or capable of splitting them cleanly. For example, if file A needs something from file B, while file B also needs something from file A, then including those things is gonna get a little tricky, right? So to this end, we can get some help with the extern modifier and this helps us declare the things that they can be used in any file, but while keeping the definition in a single place. So yeah, the compiler then doesn't reserve anything for it, since it will be encountered later, but we can both modify functions and variables with the extern keyword. Now, here's an example. If we have some implementation file, also some main file called extern.c, where we define an integer called cost and give it a value. If we want to make this integer accessible to other files via a header file called extern.h, you can do this via this extern keyword, saying, look, this is going to be, I declare here in extern.h that this is going to be used someplace, is going to be defined someplace else, not in here, right? And you'll find it later. Yeah. And here again, we are using the header file to contain the declaration of the variables that are going to be shared with other files. Now, here's a bit more complicated example I was mentioning earlier. Say, for now, we have one file, extern_func.c, where we have this integer, volatile unset, integer stop now. We define it here, and we say, look, I also need a function called bar bar, but I'll define it later. If similarly, we have a second file called extern_bar.c, where we say, look, we have an extern volatile unassigned integer called stop now. So that's going to be defined somewhere externally. So essentially what is happening here in the top file, in the extern func.c, we are trying to call a function which is defined somewhere else called bar, here in this line, and we're trying to set the value of a variable which is defined in the same file. So this bit is going to work out nicely, this not so much, because it's defined somewhere else. Simultaneously, in the other file, if you're trying to include it, here we say, look, I need something from the first file. So extern func.c needs bar from extern bar.c, while extern bar.c needs stop now from extern func.c, which is defined here. Right? So we have this circular dependence, and this is a tricky bit to do with header. Now this is a very, very simple example here. Naturally we can sidestep it, but if in larger projects where it can easily have a circle of 10, 20 header file inclusions, things can get tricky. So this is where the extern keyword comes to help us, because this code actually compiles and runs. Right? So we have no shared header file, and they depend on each other. And through the extern keyword, these things work now. So we can compile and run the program. Now, moving on from extern to constant. What's happening here is we are going to try to. Well, not try. We are going to declare some variable using this const keyword. What happens here is, once we declare a variable with a const keyword, tells the compiler this value will never change. I'm not going to change this value. So if you try to compile this program, where I here try to change the value to 200 from 100, the compiler will say, nope, you cannot do that. This is a const variable. You cannot modify that. Right? Now, okay, technically, if you really, really wanted to, you could trick the compiler by getting a reference with a pointer in there and then modify whatever's in the pointer's address, which would be sidestepping the entire idea of why we have the const keyword in the first place. So don't do that. Just don't declare the variable const if you don't want it to be constant, if you want to modify its value, right? That is really, really bad practice. Just don't try doing that. So what const provides you with is that if you have operations that are constant, they may not alter the object's state. They may not call non-constant methods. I'll show you in a minute. You can, in C++, you can declare methods as constant, which tells them that the object will not be modified. But you can call these const operations on objects. Again, this is just C++. C doesn't have objects. You can be invoked on call by const reference. So the idea would be, if you declare a reference const, you tell the compiler, I'm not going to modify this value, so I only need this as a read-only variable or read-only reference. Which is why it's useful, because for the compiler, because then it's able to optimize by knowing, look, I'm never going to have to, for example, write things back into memory in a const reference, because this is going to be read only, and whatever's back in memory is going to be fine. And it will also allow users to enforce encapsulation to write safer apps. So you know, at the very least, the intent of how a parameter is supposed to be passed into a function, as, for example, here as a read-only parameter. Now, both for sustainability and maintainability of your code and legibility of your code, but also for performance, to use the const modifier wherever possible. Wherever it makes sense, spam it. Help the compiler optimize, help yourself by declaring what your intention with the variables is. Okay. Now, I mentioned again C++ only here. C does not allow function overloading, but C++ does, so you can have the same function with different parameter values, either with different parameters, but also with const. You are allowed, C++ allows you to declare, to overload the function with a const modifier or without. And this belongs, so the const belongs into the signature, and we can overload with it with respect to it in C++. So if you put it after the declaration, so int get value and then const, this means this function will not modify the object state, whatever the object this function is attached to. This will not modify the state. This is going to be a read-only function, which will return an integer. If you put it before instead, so if you get const int get value, what you will get is a function that returns an immutable integer, right? So, and usually, so not usually, the compiler will try to use the const operations before. So if you have both of them, if it can apply use the const operation, it will function. It will get that first. Now, similarly, so we can declare function parameters as const. And this is both C and C++. And I make very liberal use of it in C, and I recommend you do the same. So if we have a reference or a pointer as an argument in a function, and we declare that one const, it means that we will never modify it again. So it is going to be a read-only variable, and not the pointer itself, but the value that the pointer is pointing to, right? So the memory the pointer is pointing to. I'm not going to modify this memory, I'm only going to read it. So you can also use it to declare global variables immutable, so nobody and nothing is trying to change it, like pi. You can also instead you can also use a define or const expression in C++, or a numerator in C and C++. Those are also the way. Well, now usually the recommendation is, if you have parameters which are passed by value instead of by reference, typically the recommendation is to not use const there, as to not spam it too much, especially if you have these small type of small types which only take a few bytes, so integers, floats, things like that. They are going to be passed by as a copy anyway, instead of by a reference. So there, it doesn't really make sense or much sense to declare them const. Although I will admit I do that nevertheless sometimes, if it makes sense to me to tell myself, look, I'm not going to modify this value. So this is supposed to be a read-only variable. Even at least performance-wise, it doesn't make sense and does a little bit of code bloat. Okay. And to finish up, we're going to talk really quickly about external libraries and what their use is. So the point being, so one of the reasons why C is so popular is that it already has a massive collection of tried and tested libraries which are available across many computing platforms. So for example, OpenGL, which What it does is it provides you a C API, so an application programmer's interface, meaning that you get, well, a collection of, let's say, functions and call signatures which you can use, and you get documentation for that, how to use them, what to do with them, how they're supposed to be used, and what to do, right? Where it does all the rest of the things for you. So it gives you commands, it gives you geometry, you can deal with them to put it into what they call their graphics hardware, which then turns it into something that displays on your machine. So instead of, writing an entire engine from scratch, how to display a window on your computer, which is the base use case when you start up a computer. You want to see some window, you want to see something happening. You don't want to have to rewrite that all the time, how to do that. You want to rely on a library which ideally has been tested across many different hardwares, many different types of underlying operating systems. You want something which is tried and tested. You do not want to keep reinventing the wheel, right? You want to be able to rely on other people, and that's where libraries come in and make life easier. So they provide functionalities that somebody else has written, but they do not provide an executable, right? So then they're not there to be executed as a program, they are to be embedded into your program. So, use of libraries, we're differentiating between two different use cases, which are called statically linked or dynamically linked. Now, if a library is statically linked, then while we're compiling and linking, actual copy of the code of the library is going to be embedded and included in your executable. Which means, so it comes with an advantage that you don't need to worry about what version of the library you have. If this library updates on your system, but you still have the old executable, which has been statically linked, the code is in the executable already, so there's not going to be any clashes or problems. The code's there, code's fine, right? It also has the advantage that we can combine different languages, so you can, if you really want to, combine different libraries between different languages, within C, C++, and assembly. So you can access these libraries written in different languages. Very often they're bound to other languages as well, like PHP, XML, and Curl. But on the other hand, we also have what we call dynamically linked libraries. So what will happen there is, instead of copying the data during linking time, a dynamically linked library will just contain one basic information. I need to fetch some information from this specific library, but you do that at runtime. And you can, for example, a useful command to know is LDD. Here, LDD. And here, for example, try it on the executable user bin PHP. It will list you the dynamically linked libraries in there, which version they have and which path they have. Right? So it will list your dynamic dependencies. If you don't have user bin PHP, try it on a different executable. You'll see how it goes. So again, dynamic linking is supposed to be included at runtime. At linking time, you just tell the compiler, you just tell your linker, I will need this, this, and this function from this, this, and this library, and this is where you're supposed to find these libraries. And the linker will check that everything works out, that these functions exist, this library exists, and then it works out, right? The advantage being that, well, we are only going to load one copy of the library loaded into memory, And this can help, for example, with updates, for example, with security updates. I mean, imagine if your entire operating system didn't have dynamic libraries. So if you change a single crucial library in there, like OpenSSL or some other crucial security fix, it will mean that you need to recompile your entire operating system and all the libraries have in there, or all the executables you have in there, which depend on them. If you link them dynamically, your system can just upgrade the library and you'll still be happy. Your executables and your other libraries are still going to be happy if they're depending on it dynamically, right? So you can upgrade without having to do way too much work. And it reduces file-space demands because you're not duplicating code all the time, or machine code, albeit, but still. Static libraries, however, on the other hand, they are directly linked into the program at compile time, at link time actually, and they will make copies of the code from the static library and make it part of the program. So once your executable is done, it's going to work like out of there, even if you remove the other library you had, because it's copied in, right? One of the advantages being that static linking can have some performance improvements. Now, how do we actually link statically or dynamically? Well, dynamic libraries are called by different operating systems. On Linux, we call them shared objects with typically the extension .so. On Windows, they're called dynamic link libraries with the extension DLL. On OS X, it's dylib. And this can actually lead to a very, very nice DLL hell with many versions of the same dynamic library you need to look for across different platforms. So yeah, that's not great, in fact. So it's best to include also your version number of the library you require, which can, to avoid very many headaches. Similarly, static libraries on Linux, they're called archives or .a. On Windows, they're just .lib, and OS X also has, just like Linux, the .a extension. So, how do we create a static library? It's in fact really not that tricky. It's just an archive containing object files. So this .o files, which a compiler creates, is just compiled objects, and you just run what we call an archiver on it. Will just essentially make a table and keep track of what's in where, what's in your object files and what's in there, right? So nothing too tricky. Just a bit of bookkeeping. So on Unix, again, the static libraries will use the .a extension. So how do we do that? Well, say for example, we want to compile two files into a library. So the first file is going to be linked list.c. So what we're going to do is call the compiler. The -c flag tells the compiler, compile it, but don't link it. And the output is going to be, I'm calling it linkedlist.o, so just an object file. Same here with another file.c. Make an output called another file.o, and -c again, compile, but don't link. And here, rcs is the command to make an archive out of this two files that we just compiled, so linkedlist.o and another file.o, and I'd like it to be named libll.a. The RCS here are basically just flags for the archiver program, and R should come with GCC, so you should have that as well. So yeah, I want to call the library libll.a. Okay. Very good. Now we have a library. Now let's use it again in an executable. Okay, so to link statically, we need basically two things. First, we need to tell the compiler or the linker which library you like to use, and Second thing is where the library is, where in your on a file system this library is. And you do this via two specific flags. One is the capital L flag is to list some directory where the library can be found, so where to look for it. You only need to add it if it's not in a system directory, so user bin include or user include. There's a handful of system directories where you will find your usual system libraries. If it's somewhere else, like in your local directory, you will have to tell it, look here as well. And secondly, the name, we need to tell it what the name of the library is, and that's what we do with the -L flag. So if you compare, if we compare here we are adding, so -L, no space, no nothing, just start writing the path, -L, bin static, there we go, and then, now you will remember we called it lib L dot A. The convention here is the compiler will understand that if you just say -L, it will add the lib beforehand and the .a after. So it will take the library name is to be LL, whereas the file name of the library should be lib L dot A. Right? And here we are creating an executable from the object file main.o, create the executable bin main static. And there we go. And then if we're on a statically linked library, you just run the program and you're good. Now, in principle, so here just as a quick aside, you can try and add code to see when a library is loaded into memory. So for dynamic loading, you can add these extensions, but just as a second side note, this is a GCC compiler extension, so it's not standard C, so it may not work with other compilers. So I'll just leave you with this code here, so you can play around with them whenever you are working on it. Okay, now we looked at the dynamic libraries. The static libraries. Now let's look at shared libraries or dynamic libraries, right? We're creating shared objects here, the -SO. Right, the -SO extension. But they need to be compiled with the -fpic option. PIC here stands for position independent code. So meaning that we don't know exactly where in memory the library is going to be loaded at runtime. So how do we do that? Let's compile our two files, linked list and another file.c, into a dynamic library. So we add the -fpic and here fpic, again the -c file for compile but don't link, and make the output file linked list.o and another file.o. And then when making a dynamic library out of it, again going to make call GCC with -shared, that'll do the trick. Provide the objects files and the output path to your file, and then lib ll.so. That's where we're at. Now, if we want to now link it dynamically, so back to, we now have a dynamic library, we want to link it. Again, we need to provide it with the compiler and the linker with two informations, what the library's name is and where to find it. And again, the capital L, provide the path where to find it, this lowercase l, and then library's name, again minus the lib and minus the .so, provide -ll, and link it again. Now, if we try to run it now, however, we will encounter an error. The problem is, at the runtime, your operating system is not going to know, well, not the operating system, your shell environment is not going to know where the library is, right? Because it's a non-standard library. It turns out there is essentially a list of system directories where it's looking for libraries, dynamic libraries by default, and if your dynamic library is not in there, it will not find it. So what we need to do is tell the system, look, look into this path as well, where the path is where you want it to do. So, and this in Bash or other similar shells like Z shell, it works by exporting what we call an environment variable. So, yeah. Or here the other example for TC shell. You set up an environment variable which is called LD library path, which usually already contains some values. Now note the backticks here. This in Bash that means execute a command. pwd is print working directory, so we'll print the path where you're currently at and just add the bin dynamics, so the directory where we're at. And for these path type variables, the convention is that the colons here are separating two different directories. So what we're adding here is another LD library path. So whatever the variable was before, we're prepending our path here. And if we do that, the system will know to look for dynamic libraries in this directory. So your current working directory bin dynamic, it will know to look for them in there as well. And if you run your program now, it'll work out. Okay, so I know I've been talking a while. We reached the end. To sum up, how do we deal with large programs before my laptop's battery runs out? We want to split big programs into many different files, where we want the declarations to go into the header files. We want definitions to go into corresponding .c or .cc for C++ or .cpp is also very commonly used files. And header files are included using this include macro wherever needed. Now we also seen the extern keyword, which allows variables and functions, we can declare them and share them via these header files. We've seen the const keyword, where the good advice is use it wherever you can. And finally, we've seen how to include and link libraries, both static ones, which are getting copied into your code at compile and link time, and dynamic libraries which get accessed only during runtime while the program is running. And with this, we've reached the end of my slides. So, thank you all for attending.